I'm P. Daphne Christina and today I'm going to be talking about waves and oscillations.
Waves and oscillations. What are waves? A wave is a disturbance or a wiggle in space and time. Wave transfers energy from one point to another. There is no transfer of mass. Then we come to oscillations. Oscillation is the periodic movement of a particle or a system. Now, what is the link between waves and oscillations? The collective oscillations of a number of oscillators is what gives us a wave. Now let's look into a few examples, shall we? Electromagnetic waves. Electric field and magnetic waves are oscillating, that is, changing periodically. Then we have sound waves. Particles of the medium are oscillate periodically. Then water waves. When a body is thrown into water, the water molecules and the height of the water surface changes periodically. Harmonic waves. These are generated by harmonic oscillators whose amplitude is directly proportional to the negative of the displacement. So as you can see these two graphs, the first graph shows us the wave when we freeze x and plot amplitude with respect to time. A second shows us the wave when we freeze t, which is time, and plot amplitude against space. Now, mathematical representation in dimensional, this is the equation that we have known so far. Y is equals to a sine kx minus omega t, or y is equals to a cos kx minus omega t, or y is equals to a e to the power I kx minus omega t. So all of these are plane progressive waves. What are plane waves then? A wave front is a plane of the wave in the same phase at time t. So when waves propagate through repeated formations of the wave fronts, we call them as plane waves. Now we have a mathematical representation for this. So we have y1 is equals to a1 sine k1x minus omega 1t along x-axis. This is plus x-axis. And y2 can be represented as a2 sine k2x plus omega t along plus y-axis. In a wavefront, we see that phase is constant because it's a wavefront. So if phase is constant, then kx minus omega t, which is the phase, is also constant. This when we differentiate this with respect to x, we have k minus omega dt by dx is equal to 0. And through this we can, when transposing k as well as dx to the other side, we get dx by dt is equals to omega by k, which is velocity, or velocity in the positive direction. Similarly, if we want to try in the negative x direction, then we can do dx by dt is equals to omega by k, but with the minus sign, since it is in the opposite direction. So this will give us negative v. Now we have vibrations of a wave. So let's take a long string which is suspended at one end to a rigid surface. Now force is applied on the other end. So what will happen? As you can see, the string vibrates, forming these waves. So these waves are what we call as transverse waves. And the particles only move along y-axis. So that is the displacement of the particle. Each of the particle of the string is a simple harmonic oscillator. Now we see the different velocities of the simple harmonic oscillators. So let's take particle velocity, which is Vp. So velocity with which the harmonic oscillators, small segments of the string as mentioned, are oscillating. So this is nothing but the velocity with which the harmonic oscillators or the particles of the string are oscillating with, as like the name itself says. Next we have phase velocity. So it is the velocity with which the surface with constant phase is propagated. This is usually along x-axis. And next we have group velocity. So it is the velocity of propagation of a wave packet, which is nothing but a collection of waves with slightly varying frequencies, that is nu plus delta nu. So for now, non-depressing mediums such as air or monochromatic waves, we see that Vg is equal to Vp, which is nothing but group velocity is equals to phase velocity. So this is about waves and their different velocities. Now we come to describing a wave. So for that we have the wave equation, which is a second order linear partial differential equation that is used to describe a wave. So dou square y by dou x square is equals to 1 by v square dou square y by dou t square. This is the wave equation. But how? Let's derive it. So now let's take away the waves produced by the vibrating string with linear mass density of mu. This is what we saw earlier when the string was vibrating. So the mass of the small segment delta x, as you can see here, is m equals to mu into delta x, because mu is nothing but the mass density and delta x is a tiny segment that we are taking. Then when we resolve the vectors, we get this following diagram. As you can see, Ft is force of tension, F1 is restoring force, F2 is displacement force, and theta 1 and theta 2 are very small angles. So now we are going to follow a 3-step algorithm. That is, step 1, we are obtaining the displacement of the small segment of the vibrating string, that is delta x. Next, step 2, we are identifying the net force being applied on the string. Lastly and finally, we have step 3, which wherein we apply Newton's second law of motion. So using Newtonian mechanics, we know that x at t, which is the displacement, is if x at t is the displacement, then F net is equals to m into dx square by dt square, which is nothing but the acceleration. So now let's begin with step 1. We know theta 1 and theta 2 are very small angles as earlier mentioned. So we can say that theta 1 is almost equal to sine theta 1, which is again almost equal to tan theta 1. And tan, as we can see when we draw the triangle, we can get that as minus f1 by ft. Similarly, when we take for theta 2, it is almost similar to sine theta 2, which is almost equal to tan theta 2, and it is equal to f2 by ft. So now we got the value of tan theta 1 and tan theta 2, and we know tan theta is nothing but slope. So the another way of finding the slope is by differentiating dy by dx. So we can equate tan theta and dy by dx at the respective points. So we have tan theta 1 is equals to dy by dx at x1, which is equal to minus f1 by ft. So this will give me the value of f1, which will be equal to minus ft dy by dx at x1. Doing the same for tan theta 2, we get tan theta 2 is equals to dy by dx at x2, which is equal to f2 by ft, and f2 will be equal to ft dy by dx at x2. So the net force is equal to f1 plus f2. Now on finding the net force, we substitute the values of F1 and F2. So we get F net is equals to minus Ft dy by dx at x1 plus Ft dy by dx at x2. So F net, I can take Ft common, so I'll get Ft dy by dx at x2 at time t minus dy by dx at x1 at time t. Now I can write x2 as x plus delta x, which is nothing but the little small segment that we took earlier. So I can say that f net is equals to ft dy by dx at x plus delta x at t minus dy by dx at x at time t. Then from Newton's second law of motion, so this is the final step that we're using. F net is equals to m d square y by dt square, which is nothing but acceleration. And earlier we had already said that the mass will be equal to mu, which is the linear mass density, into the small segment for which we're trying to find the net force in, as delta x. So we can say that F net is equals to mu delta x d square y by dt square. So now substituting F net, we are getting ft dou y by dou x x plus delta x at time t minus dou y by dou x at time t is equal to mu delta x into dou square y by dou t square. Now I transpose the term, so I take delta x towards the left side and ft towards the right side, and I get this. That is dou y by dou x at x plus delta xt minus dou y by dou x at mt, the whole divided by delta x is equals to mu by ft dou square y by dou t square. Now what I do is that we're applying the limits, that is delta x is almost tending to 0, since delta x is a very small portion of this string. So it's almost tending to 0. So when applying the limits, we see that we're getting dou square y by dou x square is equals to nu ft dou square y by dou t square. This is the wave equation. And by using dimensional analysis, we can also find the value of v, which is the velocity of the wave. So v is equals to root over ft by mu. So on substituting mu by ft with v, we get dou square y by dou x square is equals to 1 by v square dou square y by dou t square. This is the wave equation. But how do we interpret this wave equation? So let's see. Over here we see that the restoring force F is equals to minus kx in this case is very linear. Another thing is Vx, which is nothing but dx by dou x by dou t, which is the phase velocity. This is the rate of motion of disturbance along the wave. That is nothing but the rate of motion of the wiggle that is created in the wave. Then we have Vy, which is equal to dou y by dou t. So this is the oscillator velocity, that is every single particle's velocity that we saw earlier again. So simple harmonic oscillations, all of them are going through. Now we can say that that Vy is equals to dou y by dou t, which is equal to dou y by dou x into dou x by dou t by using chain rule. Then we say that dou square y by dou t square is nothing but the acceleration of the oscillator, and dou square y by dou x square is nothing but the curvature of the wave. So this is how we are interpreting the wave. That is, the first term is giving us the acceleration of the oscillator. Second term, that is dou square y by dou t square, is giving us the curvature of the wave. And in between, we have the velocity of the wave. So in general, we're getting a whole idea of what the wave is because of the equation. But now, what is the solution to the wave? The most general solution to the wave is just an equation of representation, but how are we going to find the solution to it? So over here, if you can see that the solution for this equation must also be a function of x and t, since it is with respect to x and t. So the most general form can be of the form, of the solution can be of the form f1 of vt minus x or f2 vt minus vt plus x, right? So let's first take y is equals to f vt minus x. So dou y by dou x, over here I'm differentiating f with respect to x, so then I'm getting minus f dash vt minus x. Double differentiating that, I'm getting f double dash vt minus x. So the minus sign goes away since I'm again getting another minus sign on differentiating it. Similarly, while doing dou y by dou t, I'm getting vf, which is the coefficient of t, vf dash vt minus x, and on double differentiating that, I'm getting vf dash f double dash vt minus x. This implies that dou square y by dou x square is equals to 1 by v square dou square y by dou t square, since it's an even function. Similarly, if I take y is equals to f of vt plus x and I differentiate it with respect to x, I'm getting f dash vt plus x. Double differentiate that, I'm getting f double dash vt plus x. Similarly, doing it with t, or differentiating with t, I'm getting vf dash vt plus x, and double differentiating with respect to t, we get vf double dash vt plus x. This again implies that dou square y by dou x square is equals to 1 by v square dou square y by dou t square. So in both the ways, we see that we get the same function back. So we can say that the superposition of f1 plus f2 is the most general wave equation. So we can say that f1 of vt minus x plus f2 of vt minus x is the general solution. Now let's look at this wave that we have. As we know, lambda is nothing but the distance between any two oscillators having a phase difference of 2 pi. So the harmonic waves propagate down the string with one wavelength along the x-axis during one time period along the y-axis or the time axis. So in this case, it's obvious that v has to be constant because v is equals to lambda by t. It's nothing but distance by time, and the distance is given by my wavelength and time is given by the time period. So v is equals to lambda by t is constant because it is going down, the wave is going down with one wavelength during one time period. So on looking closer to the wave, it looks very familiar. So this is nothing but the sine wave. So we can compare the wave with the sine function. We see that in sine function, the value of sine with the argument varies from -1 to +1. And in waves, the amplitude of the harmonic waves varies from -1 to -a to +a. And in sine function, we see that it repeats periodically at every 2 pi radians. In the case of a wave, it repeats at every wavelength along the y-axis. So we can see that a correlation between the sine function and the harmonic wave can be established. But this is only if theta by x is equals to 2 pi by lambda. So on taking x to the other side, I get 2 pi, theta is equals to 2 pi x by lambda. So y is equals to a sine theta, which we already know. So on substituting theta, we get y is equals to a sine 2 pi x by lambda. We also know that y is equals to a sine kx. So correlating this with the most general solution of the wave equation, we see that y is equals to a sine 2 pi by lambda x plus or minus vt. So y at x and time t is equals to a sine kx plus omega t, because when we take 2 pi by lambda within the brackets of x plus or minus vt, we see that we'll get 2 pi x by lambda plus or minus 2 pi by lambda vt. So we can take 2 pi by lambda as k and 2 pi by lambda v as omega. So the above is the solution to the wave equation. This is what we have as the solution. And with that, we have now described or found a way to interpret a wave. Now let's come to the next topic, which is wave impedance. So what is wave impedance? When a wave travels in a medium, the medium opposes the propagation of the wave. This opposition is what we call as wave impedance. There are two factors which affect this. We have inertia, which is the mass of the system resists any change in the state of motion, and elasticity, which is the tendency for it to restore its shape. Now, Z or impedance is given by the formula Fy by Vy. As you can see, we have a wave next to it to denote what is what. Fy is the displacement force, Ft is the force of tension. So we see here that Fy is equals to minus Ft sine theta. So this is which we get by drawing the triangle and getting the vectors. Now theta is very small here, so I can equate Fy to minus Ft tan theta. So I get that since tan theta is nothing but the slope, I can write that as minus Ft dou y by dou x, which is nothing but the slope. So y we know is a is equal to a sine kx minus omega t, which we just proved. So now on differentiating this, I can say that dou y by dou x is equals to ka cos kx minus omega t. So the coefficient of x comes out. Similarly, when I take Vy is equals to dy by dt, so I have to differentiate y with respect to t. So in this case, I will get minus omega a cos kx minus omega t, since minus omega is the coefficient of t. Now z is equals to minus ft dou y by dou x divided by dou y by dou t. Now how did I get this? We just derived the value of Fy, that is minus Ft dou y by dou x, and Vy we just saw right now is dou y by dou t. So since z is equals to Fy by Vy, I am dividing the two. So on solving this, we see that we're getting z is equals to Ft k by omega, which is again equal to Ft by Vx or Ft by V, and it is also equal to root over mu by Ft. This is equal to mu V. Now we come to chin and transmission. So let's take two mediums that is separated by a surface. So when we have incident waves coming from medium 1 and hitting medium 2, or the surface between medium 1 and medium 2, we see that most of the waves are actually reflected back, but some get transmitted into medium 2. So what exactly happens when the waves strike medium 2? Impedance suddenly changes. But how does this affect the wave? So over here, if you see, yi is nothing but the equation for the incident wave, can be given by a1 e to the power I kx minus omega t. And then for reflected waves, yr is equals to b1 e to the power I kx minus omega t. And for transmitted waves, yt is equals to a2 e to the power I kx minus omega t. Out of this, we have the transmission coefficient t, which is equal to a2 by a1, and again equal to 2z1 by z1 plus z2. And we have reflection coefficient r, which is equal to b1 by a1, or equal to z1 minus z2 by z1 plus z2. Now we will apply the boundary conditions to the following. So the first boundary condition is that the displacement y must be continuous. So we can say that yi at x is equal to 0 plus yr at x equal to 0 is equal to yt at x equal to 0. So on writing the equations for each of the waves, we see that a1 e to the power I omega t, kx is removed over here because x is equal to 0, plus b1 e to the power I omega t is equals to a2 e to the power I omega t. Through this, we are getting a1 plus b1 is equals to a2. So this satisfies our first boundary condition. Next, we see that the transverse force, that is Fy, must be continuous at the boundary, which is x equal to 0. So we know force is equals to ma, At the boundary, we see that we're just taking a small segment of the string or a segment of the wave, and at this part, the mass is almost tending to 0. So if f is equals to ma, then a should be tending to infinity if mass is tending to 0. But this is clearly not possible in real life, right? So we take ft dou by dou x of yi plus yr at x equal to 0 should be equal to ft dou yt by dou x at x equal to 0. Then on applying the equation, since x equal to 0, we see that the value of x is, then on applying the equation we get minus a1 k1 ft plus b1 k1 ft equal to minus a2 k2 ft. So if I take k1 as omega by, if I take k1 as omega by v1, since omega is constant throughout the entire reflection as well as transmission, we see that omega will be the same on both the sides of the equation, so it will get cancelled. Hence we are left minus a1 f1 by v1 plus a b1 ft by v1 equals minus a2 f1 by v2. This on solving will give me z1 a1 minus b1 equal to z2 a2. Now when we look into two special cases, first we see when z2 is at infinity, it implies that x is equals to 0. So over here no transmission takes place at all. The incident wave is completely reflected with an angle of pi. That is, there is a phase difference between the incident and the reflected waves of 180 degrees. So r is equals to b1 by a1 will become minus 1. The special case 2 is when z2 equals to 0. So in this case we see that x is equals to 0 is the free end of the string. So here we have r1 is equals to 1 and t is equals to 2. Now we come to standing waves, which is the last topic for our session. So here we take a string which is suspended at both the ends to a rigid surface. Since it's a rigid surface, at both the ends of the string we have a medium with impedance that is equal to infinity. So now if we pluck the string at any point, say y over here, we see that the progressive waves gets completely reflected at infinite impedance with a phase change of pi. This we saw earlier in the special case of impedance. So the wave of frequency omega with an amplitude a in the plus x direction and an amplitude b in the minus x direction will be given by y at x comma t equals to a e to the power I kx minus omega t plus b e to the power I kx plus omega t, since it is in the negative x direction. So now let's apply the boundary conditions. So first condition is y is equals to 0 at x is equals to 0. So since y is equals to 0 over here, I can put 0 is equals to a plus b e to the power I omega t, and then I get that a is equals to minus b. So now if I substitute this within the equation, that is y at x comma t equal to a e to the power I kx minus omega t minus a e to the power I kx plus omega t. So I can take a e to the power I omega t outside, and I will have e to the power I minus kx minus e to the power I kx. So on solving this, I will get y is equals to minus 2ia e to the power I omega t sine kx. The second boundary equation is when we have y is equals to 0 at x is equal to L. So sine kl is equals to 0. This implies that sine omega L by v, this is nothing but sine omega L by v. So I can take omega L by v and equate it to n pi because sine is 0 at every n pi. So omega n is equals to n pi L by v, and I can substitute omega as nu by 2 pi nu. So nu is equals to nv by 2l, which is also equal to v by lambda n. Through this, I also get the value of L, which is equal to n lambda n by 2. So now over here, the frequency that we have obtained through this equation is what we call as normal frequencies or eigenfrequencies, and these are unique frequencies. So let's see a few characteristics of standing waves. Firstly, standing waves arise when a single mode is excited and the incident and the reflected wave superimpose. So energy is carried in one direction is exactly equal to the energy that is carried in the opposite direction. Total energy flux, that is the energy carried per area per second in a standing wave of a system, is zero. So standing waves are stationary waves that oscillate in time, but its peak amplitude profile does not move in space. It's very important. So now we have the different modes of vibrations. So for a given harmonic where n is greater than 1, there will be n minus 1 points on the string which are always at rest. So these points of zero displacement are what we call nodes. So as you can see in the figure given below, that the first wave that we see is the fundamental frequency. Here n is equal to 0. So n minus 1, which is nothing but 1 minus 1 equals 0. So there are 0 positions on the string which is at rest. And the same way I can do for the second harmonic frequency. So over here n is equals to 2. So n minus 1 is 1. So there is 1 point which is at rest. Similarly, this will be going on to how many ever frequencies that we want. The same pattern is followed. So now what is the mode of the nth node? Y is equals to minus 2ia e to the power I omega t sin x, which is what we just derived. So complex amplitude C equals minus 2ia e to the power I omega t. So sin kx is nothing but the this is just why when we relate it to the formula y is equals to a sin omega t or a sin kx. The a over here is nothing but the amplitude, which is nothing but a complex amplitude. So if I take magnitude of C alone, I will be doing root over modulus of C square, which is equal to root over minus 2ia e to the power I omega t into 2ia e to the power I omega t. And this will give me 2a. So the amplitude of the nth mode is equals to 2a. With this, we come to the end of the chapter. I hope everything is understood. Thank you for staying along for this long.
Thank you for watching the video.